So, welcome to our next session. So, integrated circuit. Myself, Mohammad Khadir, working as assistant professor in EC department. Today, we are going to see our next topic is differential amplifier. So, it's a part of one of the block which is required to get more gain in our IC741, which is operational amplifier. So, today we are going to see that what is mean by differential amplifier and what are the configurations are there, types are there, and we are going to be see one of the analysis part of our differential amplifier, part of the configurations. So what is mean by differential amplifier? The name itself, it mentioned that difference between your given inputs of a integrated operational amplifier circuit. So the differential amplifier, it is going to be difference of your given dual input. It is required a two input circuit. It is required two input circuit where we are applying two inputs V1 and V2. That output will give that difference between the two inputs, which is V0 is equal to V1 minus V2 identically. So differential amplifier is a type of electronic amplifier circuit which is gives the difference between two input voltages, which is gives the difference between the two input voltages. So a differential amplifier, also known as a difference amplifier, is a type of electronic amplifier that amplifies the difference between the two input voltages. And here, this is the basic diagram of a differential amplifier, circuit diagram of differential amplifier, where we can see that where we are going to use two transistors as a V1 and V2 for, we are going to be apply input to the two transistors Q1 and Q2. And we are going to be observe the output across the collector pins of Q1 and Q2. So the difference between the voltage across the collector Q1 is gives V01 and V02 will gives the voltage, output voltage across the resistance collector pin of Q2 transistor, which is O2. So by that, the output voltage will gives the difference between the two applied input voltages. As a two common mode transistors we are going to be used, which are Q1 and Q2, are matched devices we are going to be used. This is the one of the character of a differential amplifier circuit, where we are going to be used Q1 is equal to Q2. And we are going to be give two inputs across the base terminal, which is V1 and V2. We are going to be observe the output voltage across the collector pins of a Q1 and Q2 transistor. In between, the equal difference between the two applied input will give as the output voltage V0 is equal to V1 minus V02. And if you observe a difference, or the other type of definitions are mutual, same definitions. If you observe that from the different nodes, where the differential amplifier is the analog circuit or amplified circuit of a two inputs, which we are going to be give as V1 and V2, and the output will gives as V0, which is equal to V0 is equal to V1 minus V2, along with a amplifier, which AD gives as a gain of your amplified circuit. The gain which is gives as VD is equal to output by difference of input, where VID becomes V1 minus V2, which is the differential voltage of your applied input voltages to the Q1 and Q2 transistor in a differential amplifier circuit. And the formula, the output will gives expressed as gain, the product of gain with a difference between the two applied input voltages, which is equal to AD is equal to VID. VID becomes V1 minus V2. And there are the configuration or types of, if you observe the differential amplifier, we are having the four basic types or configurations are classified of a differential amplifier, or BJT differential bipolar junction transistors we are going to use. So we can call it as BJT differential amplifier also, which is classified into four types, which are dual input balanced output, one type differential amplifier. dual input unbalanced output differential amplifier, and single input balanced output differential amplifier, and single input unbalanced output differential amplifier. There it will gives the different types of the configurations are classified, where we can see that the gain is going to be increased, how it is going to be amplified, what is the difference, everything will be seen here coming. So here if you see that first one, dual input balanced output differential amplifier, it gives that the name itself we are mentioning that dual input. Dual means two inputs we are going to be applied, and balanced output. So the balanced output means the output between the two collector pins of your Q1 and Q2 transistor will give the balanced output, which will be gives as V0 is equal to V1 minus V2 along with the gain of your product term AD. Similarly, in an unbalanced output means we are going to be observed output across only one of the collector pin of any Q1 and Q2. That is the difference between the balanced and unbalanced. Where we will give the dual input, same inputs, but the output will observe only across any one of the collector pin of your Q1 and Q2 transistors. And a single input balanced output differential amplifier. Here we are going to be give the single input where we are applying only either V1 or V2 as a input. Any one of that remaining secondary one will be defaultly becomes a grounded, nothing but equal to 0. Means here we are going to be give only single input, and we are going to be observe the output difference between the two collector pins of Q1 and Q2 transistor. In similarly, single input unbalanced output differential amplifier means where we are applying any one of the input out of the V1 and V2, and then remaining secondary one other input will becomes grounded. By the way, we are going to give that single input, but we are going to be observed output also across any one of the transistor collector pin, where we will get an output is a gain with input difference. So means here in this one V0 becomes equal to AD into V1 minus V2. In this, if you consider V2 becomes 0, then we are going to be give V1 as a single input one. By that your output will becomes AD into V1, because secondary one becomes 0. In such a way that we are going to be observed our output, and we will calculate a gain differential amplifier gain AD. So by that we can express gain as differential amplifier is V0 by V1. So this is about the single input brief idea of your dual input balanced output differential amplifier, dual input unbalanced output differential amplifier, and single input balanced output differential amplifier, and single input unbalanced output differential amplifier. In this one, first one we have seen this. Here we are going to be consider Q1 and Q2 are matched term transistors, same characterized similar transistors we are going to be consider to give the two inputs. Dual inputs V1 and V2 are a dual input and balanced output. The output will be difference between the across the collector pin of Q1 and Q2, which will be gives as your output as V1 minus V2 along with some amplifier gain AD. So here the output balanced means we are going to be observe the output in between the collector pins of your Q1 and Q2 transistors. And unbalanced one means here we are going to be give dual input. Both the inputs we are going to be applied, but output will be observed only across the one of the collector pin of your output transistors Q1 and Q2. And next one, single input balanced output differential amplifier. In this one, we are going to be give V1 and V2 are a dual input, but single input means we are going to be make any one of the input becomes grounded, nothing but equal to 0 by applying V1 as a single input, where we will observe that balanced output means the difference between the two collector voltage across the two collector pins of Q1 and Q2. And unbalanced one, where we are going to be see that this is the balanced one. If you are observe that unbalanced one means we are going to be give the output will be measured across that any one of the collector pin across the Q1 and Q2 transistors, any one of them. We are going to be observed, let us consider Q2 is the output transistor. So I am going to be consider collector pin of Q2 transistor, output voltage across the collector pin of your transistor Q2, which will be gives output as a single input is like. So it's such a way that we are going to be see that, and next we are going to be see that analysis part of dual input balanced output differential amplifier. Dual input balanced output differential amplifier analysis. So what is mean by this analysis? By doing the analysis, what we can be measure means, so in AC and DC analysis, there are two type of analysis can be do for any electronic and electrical circuit. So when you are going to be do the analysis part, if you are doing AC analysis, there we have to be do the DC voltages or DC supply becomes 0. Then we have to do the our analysis part for the measurement of gain and input impedance, output impedance of your electrical or electronic circuit. In such a way that if you observe our differential amplifier, while doing AC analysis, we have to calculate gain of the differential amplified circuit and input resistance and output resistance. We have to be measured of your dual input balanced output differential amplifier. In DC analysis, we have to make as a AC supply should be 0. Wherever that you are applying a AC supply, it should become 0. Then we have to analyze our circuit of your equivalent circuit of a differential input dual input balanced output differential amplifier. Then we have to be measure in DC analysis are operating points of your Q1 and Q2 transistors. What are those operating points means? If you observe our differential amplifier circuit, these Q1 and Q2, where we will get IC is our operating point, one of that, and another one is VBE as another operating point of VCEQ and ICQ. ICQ means current across the collector pin, and VC means voltage different collector to emitter. The voltage drop across the collector to emitter will be gives that your VC operating point, and the current across the IC will be gives your operand. Where will be operating, your transistors are going to be operating in I current versus voltage will be gives your operating points. So that analysis part we are going to be do in the dual input balanced output differential amplifier. So in our AC analysis, we have to measure gain, input resistance and output resistance, and coming to the DC analysis, we have to derive a values for ICQ and VCQ. That we will do. So in AC analysis, we have to perform the circuit while making a DC supply becomes 0, and draw the equivalent circuit, then apply some nodal analysis or by applying some KVL and KCL. Then we will calculate our gain and input resistance and output resistance by doing this AC analysis. So this is the way, the steps we have to be followed to derive expressions for the gain and input resistance of a differential amplifier. So now we will see our dual input balanced output differential amplifiers AC analysis. Dual input balanced output differential amplifier AC analysis. So how to do this AC analysis? What is the steps we will see now to measure a gain and input resistance and output resistance of your differential amplifier circuit. Let me draw the first circuit of your dual input balanced output differential amplifier circuit. So we have to consider two transistors, matched pair transistors, Q1 and Q2, where this is base terminal and this is emitter terminal and this is collector terminal. Now applying some VCC. Here we are applying negative VE along with some inputs V in 1 and this is V in 2. Dual input balanced. So output will be across collector pins. Now here this is it to resistance of your emitter terminal, and this is here we have to consider that internal resistance of base terminals will becomes, let us consider Ri2 and Ri1, and the collector resistance Rc, both are parallel to, so let me consider Rc. Rc is a collector resistance of your Q1 and Q2, and this is becomes Re. Now the current across this Re becomes, so from here the current is coming IE1, and from the half here emitter 1 Q1 transistors, and here emitter terminal of Q2 transistor where current will becomes IE2, let us consider. So from here the total current will becomes IE1 plus IE2, and current passing through the base terminal will becomes IE1 of Q1 transistor, IB2 becomes base terminal of Q2 transistors, and current across this resistance of your collector pins becomes IC1 and IC2. So if you consider this dual input balanced output differential amplifier circuit, where coming to that basic configurations of your transistor will be that output the amplification factor beta, so it is a common emitter configuration if you observe. So where this common emitter configuration, the amplification factor of common emitter configuration beta will be expressed as output current by input current. So collector output current by base across the current, which is called IB. So by this we can be seen this, that output current will be almost equal to the emitter current. So IC is approximately equal to IE, which have seen our basics of your common emitter configuration of your BJT transistors. If you analyze that one, from there we can be express that collector current is equal to emitter current, IC approximately equal to IE. So now I can be express beta is equal to IE by IB also. Okay, so this is one. And what is the output? Output will becomes V0 is equal to V1 minus V2. V1 minus V2. So by using these prerequisites, we are going to be derive a expression for gain by doing the DC analysis of your dual input balanced output differential amplifier. So for that, I need to derive first equivalent circuit. Equivalent circuit. So how to draw this equivalent circuit? So let me start from this here. So when you are going to do the DC AC analysis, DC supply should becomes 0. DC supply should becomes 0. So further, first this will become 0 and this will become 0. Both will becomes, make it as 0. So then we have to consider, so from here this is a resistance Re, common point Re. So from here, if you consider the path, the direction of in this way, the direction in this way, then what we have to draw? This is Re. The current will across this Re is equal to IE1 plus IE2. Now, if you go on through this one, so next will becomes here base resistance. So this is the base resistance Ri1 input resistance. Then we are connected to input supply. So here input supply is AC. So we have to be consider it one. It should not become 0. Where this V is a negative supply. So when the DC supply becomes 0, AC in the AC analysis, DC supply becomes 0. So make it at ground. Then we have to be consider continuously, it goes to the collector. So across this collector, the resistance is RC. It towards the VCC where it is becomes grounded 0. So I make it as is ground 0. Now we should not forget that here this internal current is IB1 and here the collector current is IC. And emitter, this emitter consists internal resistance of a dynamic resistance or internal resistance of your Q1 and Q2 transistor. The dynamic resistance we can be expressed as the emitter terminal, which is becomes Re. It will becomes Re internally. It will be so it will be available the analysis while doing the AC analysis. we should not forget about this one. The dynamic resistance of a dual input balanced output differential amplifier. In a differential amplifier, RE becomes dynamic resistance of a emitter pin. So then the current across the emitter will becomes IE1. Similarly, the same symmetrical is present across this Q2 transistor. So whatever that pins are available, resistance, impedance, everything is available, it will be reflected in the other side also. So if you gone through this direction, so we have to be considered as a first emitter or a base input resistance, which will becomes Ri2. So current across this Ri2 becomes Ib2, and input supply becomes, here it is V in 1, and now it is becomes V in 2. Then it's towards the collector pin, so it's same as collector pin, which will becomes RC, and towards the VCC it will becomes ground because it's a DC supply. Now internal resistance of here another emitter terminal of Q2 transistor will becomes RE, dynamic resistance of emitter pin, which is the current across this dynamic resistance becomes IE2. Here it is IE1, in the IE2. So everything will becomes clear. Now current across this collector pin becomes IC2. So this is the equivalent circuit of your dual input balanced output differential amplifier, where we have to be calculate our gain and input resistance, output resistance. So for calculation of gain, we have to do the nodal analysis otherwise we can apply a KVL to the loops, irrespective of the loops, where we can calculate our gain. So first we will write the expression for two loops. Let us consider this is one loop, loop 1, and this is another loop, loop 2. So by using this one, we are going to be write a expression. So let me write. Now let us consider loop 1. Apply a KVL to the loop 1. So how will you write? KVL is nothing but Kirchhoff voltage law. Sum of entering voltage will be equal to sum of leaving voltages. So I am going to be write V in 1 voltage. So V in 1 voltage is equal to leaving voltages. So Ri1 into Ib1 plus IE1 into RE, dynamic resistance across the emitter, then plus here this one IE1 plus IE2 into RE. Okay, so this is the loop 1, where we are going to be consider from here input voltage is apply V in 1 will becomes is equal to leaving voltages, which will becomes that from the base to the RE. So from base, which is Ri1 into Ib1 plus dynamic resistance Re into IE1 plus sum of this total resistance of your current will becomes IE1 plus IE2 into Re. So this is the expression. Now if you simplify we know the formula, which is beta is equal to amplification factor, beta is equal to IE by IB or IE by IB. So by using this expression, IB can be represented as IE by beta. Now I am going to be apply this amplification factor into this expression. So Ri1 into Ib1 becomes IE1 by beta plus IE1 into Re plus IE1 plus IE2 into Re. In similar way, if you make it out common IE1 expressions, current will becomes make it out common IE1, then what you will get Ri1 by beta plus Re plus capital Re. I am going to be split this expression into the two parts, IE1 into Re plus IE2 into Re. By that you will make it as IE1 is common, then remaining term is IE2 into Re. In similar way, now what is beta? The beta value of your dual input balanced output transistor, common emitter transistor beta. Common emitter transistor, the current amplification factor beta value becomes in between the more greater than of 150. So it's a maximum value. When the denominator is maximum, it will be a very small value. The ratio of Ri1 will become very less, beta very far much less than of Re plus Re. So based on this one, I am going to be simplified. V in 1 becomes as IE1 into, this will be neglected. When beta is maximum compared to your Ri1, then the ratio will becomes very small. The smaller value I am going to be neglected. So by that we can be represented as Re plus Re plus IE2 into Re. So let us consider this is the V in 1 expression for V in 1. So for of a loop 1 analysis by doing this KVL, by applying the KVL. In similar way, if I am going to be write a V in 2 for the by doing the loop analysis of second one, loop 2. So what do you have to do? Across the loop 2, just you apply to KVL, Kirchhoff voltage law. So then V in 2, sum of entering voltage is equal to leaving voltage. So V in 2 is equal to, leaving is Ri2 into Ib2, Ri2 into Ib2 plus Ib2, IE2 into Re, dynamic resistance of your emitter terminal of your Q2 transistor, plus sum of this current into total resistance, which is IE1 plus IE2 into Re. Now I am going to be simplifying the same way of loop 1. So IB1 can be represented as Ri2 into IE2 by beta plus IE2 into Re plus IE1 plus IE2 into capital Re. Now if I simplify this one, V into becomes, make it out IE2 is common. So by that Re capital Ri2 input resistance Ri2 by beta plus Re plus capital Re will plus IE1 into Re. Now this will becomes neglected, same by using this expression. Beta factor will becomes very high. So the fraction, the ratio will becomes very smaller value compared to Re plus Re. So I am going to be neglected. By that V into can be represented as IE1 into Re plus IE2 into Re plus capital Re. So this is the second expression of your loop V in 1 and V in 2. Clear? So next, by doing these two expressions, let me write once again. V in 1 can be represented as IE1 into Re plus Re plus IE2 into Re. In similar way, V in 2 becomes represented as IE1 into Re plus IE2 into Re plus Re. So these are the two expressions of voltage, input voltages V in 1 and V in 2. By doing some mathematical analysis, we can be able to calculate our IE1 and IE2 values. The current across the emitter terminals of your both the transistors will be calculated by doing the mathematical analysis as a matrix Cramer's rule. I'm going to be applied Cramer's rule, so we can able to easily calculate our current across the emitter junctions of Q1 and Q2 transistors, which will becomes expressed by using these equations as V in 1, V in 2 is equal to your resistance Re products are factors Re plus Re, and this is a Re, and similarly second expression Re, and here it is Re plus Re with the multiplying factors current terminals IE1 and IE2. So by what is this Cramer's rule? How can we able to calculate? Means we have to calculate IE1 and IE2 current across the emitter terminals of your both the transistors Q1 and Q2. Further, if you want to calculate IE1, so then this V in 1, this column will be replaced with the first column of your matrix. So which can be expressed along with the determination of your AD and BC. A, B, C, D elements if you are considering the matrix. So the determination will be gives AD minus BC. So for that, how will you express V in 1 and V in 2, then RE, then RE plus RE by determination AD minus BC. So RE plus RE whole square minus RE square. Yeah, so by that AD minus RE plus RE into RE plus RE plus RE whole square minus RE into RE square. So if you simplify this one, V in 1 into RE plus RE minus V into RE by RE plus RE whole square minus RE square. So now IE1 becomes, if you expand this one, V in 1 RE plus V in 1 RE minus V into RE whole divided by, expand this denominator term, which will be gives RE square plus RE square plus 2 into RE plus RE minus RE square. So RE square will be get cancelled. Then it will be gives, if you observe this common terminal, here RE is there. So V in 1 RE plus, if you make it out RE is common, it will be gives as V in 1 minus V in 2 divided by RE square plus 2 into RE. So finally IE1 can be expressed as V in 1 into RE plus RE into difference between the inputs V in 1 minus V in 2 whole divided by, if you make it out RE is common out here, RE will becomes, make it out common, so it will becomes RE plus 2 into capital RE. This is the expression for current in terms of your input voltages. So this is for IE1. Similarly, we have to be calculated for IE2 also. So for IE2 can be expressed like this. So this column will be replaced with second column of your matrix. Then you have to apply a determination in similarly how we have calculated in IE1. So by that, what we have to express out here. So here it will becomes RE plus RE, and here it will becomes capital RE. Now here V in 1 and V in 2, then determination will becomes same as RE plus RE whole square minus RE square. Denominator will be same for the both that current. So IE1 and IE2. Now you simplify this one. So if you multiply V in 2 into RE plus RE minus V in 1 into RE by, expand this one, RE square plus RE square plus 2 into RE minus RE square. So plus RE square minus RE square will be cancelled. So in similar way, IE2 can be expressed here. V in 1, if you make it out common here, V in 2 RE, V in 1 RE. So if you make it out RE is common, V in 1 minus V in 2 plus V in 2 into RE all divided by RE square plus RE, if you make it out common, RE square plus 2 into RE. So similarly, it will give us as V into RE plus V in 1 minus V in 2 into RE whole divided by RE, make it out common, RE plus 2 RE. So this is the fourth expression of your collector current across the second emitter transistor, which is Q2. So now we know this IE1 value here, third one, and we know this IE2 value. Okay. Now what is our main importance is we have to calculate it gain. So for that gain we need to know that output voltage. So what is that output voltage here? If you observe this circuit out here, what is the output voltage here? Output voltage becomes, if you analyze this equivalent circuit across these collector pins C1 and C2 will becomes is RC into IC1, then minus RC into IC2, current across the Q2 transistor of a collector pin, current across the collector pin of Q1 transistor. So by that RC make it out common, IC1 minus IC2. So by we have seen this one, RC into IC1 minus IC2, the output voltage will becomes. So from this output voltage expression, if you observe this, the current across the collector pin is equal to current across the emitter pin, I. So based on this one, if I replace this expression with emitter current, which will becomes I1 minus I2, where we know these values I1 and I2. Now from third and fourth equations, we have to be substituted I1 and I2 in the given output voltage expression. So for that, output voltage is equal to RC into IE1 minus IE2. So what is our IE1? Which is RC into, if you observe IE1, V in 1 into RE plus RE into V in 1 minus V into. V in 1 into RE plus V into RE into V in 1 minus V into whole divided by RE of RE plus RE. Now this is I1. Similarly minus it will becomes V in 2 into RE plus RE into V in 1 minus V into whole divided by RE of RE plus 2RE. So minus will becomes placed out here. So based on that one, directly have substituted here. So RC is here. Now denominator is same. So when you are doing LCM, you will get the same denominator, RE plus RE. Now add the numerator terms, V in 1 into RE plus, here RE V in 1, here RE V in 1 minus V in 2, both are the same term. So directly I am writing 2 into RE into V in 1 minus V in 2. Minus V in 2 into RE. So if you make it out common in this RE, so what you will get? RC into RE common. So V in 1 minus V into V in 1 minus V into plus 2 into RE into V in 1 minus V into whole divided by RE into RE plus capital RE. So then what is your output voltage here? RC is equal to, here RE, here 2RE. This is both the same terms, V in 1 and V in 2. So V in 1 minus V in 2, if you make it out common, so your expression will becomes RE plus 2RE whole divided by, this is 2RE. So denominator will becomes 2RE. Here it is 2RE. So RE into RE plus 2RE. So by that, this numerator term, denominator term will be get cancelled. By that your remaining expression becomes RC by RE, where RC is your collector resistance of your transistor and RE becomes dynamic resistance of your emitter junction of Q1 and Q2 transistor will be gives with V in 1 minus V in 2. So V in 1 minus V in 2 means difference between two input voltages, which will be expressed as V0 becomes RC by RE into VID. Let me consider VID is equal to V in 1 minus V in 2. So by that, voltage will becomes expressed as RC by RE into VID, where VID is a differential difference between the two input voltages, which will be expressed as VID is equal to V in 1 minus V in 2. Now we done. This differential input is a input, so it's coming, the denominator will be expressed as VID, which will be gives as RE by RE. So where V0 output voltage by difference of input voltage will be gives as gain of the differential amplifier, which can be expressed AD is equal to RC by RE. So this is your gain of differential amplifier, which is a dual input balanced output differential amplifier gain, which can be expressed as AD is equal to RC by RE, where RC is a collector across the resistance of a collector pins, which is Q1 and Q2, both are matched terminations, so Q1 is equal to Q2. When it is a matched pair transistor, your collector resistance will become same, RC1 is equal to RC2 is equal to RC. And with dynamic resistance also the same, the emitter dynamic resistance across the emitter junction of Q1 and Q2, which will be the ratio of collector impedance by dynamic resistance of emitter junction of your transistor will be gives as your differential amplifier gain, which is AD is equal to RC by RE. So this is about a AC analysis of dual input balanced output differential amplifier. So in the next we will discuss about DC analysis of dual input balanced output differential amplifier. In that we have to do that in DC analysis we have to calculate that collector current and voltage across the collector to emitter junction, which is a VCEQ. Both that operating points we have to be calculated, VC and ICQ, by doing the DC analysis. When you are going to do the DC analysis, AC supply should becomes 0. AC supply should becomes 0. So for that, nothing but we have to do that input. Both the input signals has to make it as 0. V in 1 and is equal to V in 2 is equal to 0. Then we will calculate the DC analysis of your equivalent circuit of DC analysis circuit of dual input balanced output differential amplifier. So we'll see in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.